Okay, cool. So, hi everyone. I'm Katie Rocha, and my talk is Newer Isn't Always Better, Investigating Legacy Design Trends and Their Modern Replacements.
And you did start recording?
Cool. Are we good? Cool. So, here's just a little bit about me. So, I'm a software engineer at Atomo Space with Keith, and I'm currently working in a C++20 code base. However, before I've worked on a 20-plus-year-old code base that's been through all the legacy struggles of trying to improve. And so with that, I've kind of taken some of the knowledge that I've had from doing genealogy at home with my family and looking into our family's past and become kind of like, let's take that and apply it to software. So with this, we're going to be looking at kind of design trends and trying to understand what's going on, and maybe we're looking at the old patterns not as critically or so critically, and we aren't doing the same criticality at the new patterns. So yeah. So with that, my initial discovery, so I like to look at the past and kind of understand what's going on. With that, I think we sometimes look at the new pattern and are like, oh, it's really shiny, it's really awesome. And so we should just use that instead and move over, not looking at the faults and the issues with the new patterns. And we tend to make our initial evaluation, move over, stick with it, and deal with it. And like, if we're looking at that, that happens everywhere. One good example is like Stanley cups, like the water bottles. Everybody has one. And so like you have this massive shift of everyone moving from like Hydro Flasks or whatever to Stanley cups. And so like, is that really the best water bottle, or does the other one work? I don't know, but we're doing the same thing potentially with our source code. Cool. So with that, kind of have a process that we're going to work through here. So we're going to kind of look at a generalized timeline, kind of looking at how everything lined up and why the trends kind of transitioned. And then we're going to look at the original trend. What was it? Why was it used? Look at the new trend, do the same thing. We're also going to look at the original code, kind of get to look at the solution. And with this is like, I want it to be super interactive. So let me know what you think with it. We're going to try and figure it out together if the new solution and the old solution have any issues, kind of what's going on here, what sucks, what doesn't suck, what could we do better, and kind of understand and come to a conclusion as a group of, was this actually, should we be moving from the past to something new? Or are we really better off looking at the past thing and recognizing its benefit and continuing to use it? And then afterwards, we're going to do a little bit of analysis and kind of look big picture at it. So I have 3 different ones we're going to go over today. The first one is global interfaces and global state, which is everyone's favorite thing to deal with. So with that, we have kind of 2 big use cases for globals. So our first one is interfaces. This is things like logging, things where we have to deal with external resources, potentially dealing with a different language and trying to connect between the two, resource management. And so the whole idea with this is we're trying to deal with something that we can't just like wrap up and deal with ourselves, but we have to deal with something else. And then our other use case is global data. And so this is things like your init parameters, say you're reading them from Excel and sharing them with everybody else, or things like state parameters. So I work in the space industry, so things like position, velocity, and acceleration is something that would be a good example of something that you'd have as a global object that you'd share with everybody else, because everyone needs to know those three values, and so you're going to share it, but then you're also going to want to update it with one person updating it and everyone getting the update. So here's kind of a generalized, vague timeline of kind of what's going on. So we started with our global variables, and then we moved to our design pattern singleton. So design patterns is a book that came out in the 90s, and it was kind of the quintessential object-oriented, the start of the object-oriented kind of, here's a bunch of different patterns we can use, and we can use them in a variety of different cases. And in C++, they showed implementations of them. And so this is your quintessential 90s C++ implementation. And then we have the Myers singleton, which was kind of a change on that and added a bunch of improvements. And then we also have monostate, which was a different object-oriented pattern that can be used for kind of global state. And then we also have dependency injection. So our first trend is a singleton. And so the idea with a singleton, so I'm assuming everyone's used a singleton before. Raise your hand if you've used. Okay. Maybe raise your hand if you haven't used a singleton. Okay, cool. So the idea is that we have one copy and we're trying to access it, and we usually access it through a get instance or instance function. And what's really nice about that is you can look at a piece of code and you see that get instance and you're like, that's a singleton. And so that identifiable moment is really important in knowing what it is versus looking at it and let's say we didn't call it get instance, but like access the thing. You probably wouldn't instinctively think that's a singleton. And so since we've kind of kept everything consistent with that get instance, it's really easy to tell exactly what this pattern is and that it's accessing some sort of global data. However, with that, it becomes really hard to test because you have this global object that can be accessed by pretty much anyone, and that causes you to have potential someone else can modify something, causing the state to be not what you expected it to be. So that can cause issues when it comes to testing. It's also quintessentially overused. So like, I guess with that, who has a potentially negative feeling about singletons? So with that, I guess we'll ask the other, who has a potentially positive feeling about singletons? We got one. So with that, it comes up that we need to figure out how to, maybe the singleton deserves the wrap, maybe it doesn't. So cool. So here's some code. So we're going to kind of walk through both of the codes. So on the left is the design pattern singleton. You can tell it's kind of 90s style singleton, but I made it fit all in one slide. So we had to use some modern stuff to get it all in header. So like our 90s style singleton, and then on the right is the Myers singleton. And so with that comes with some pros and cons. So does anyone see anything fun that they'd like to point out with either of the singletons?
Never free that one.
Yeah. So we never free the one on the left, and then there should be a not on the if instance. But like it's null, so it's probably okay, right?
No,
Or no, doesn't it not?
yeah.
Oh, okay. I'll fix that. That's on me. Cool. Thank you. So with the new, it'll probably be cleaned up by the OS, hopefully, when the program ends. So it's probably fine. Like your modern OS, it's probably going to be okay.
Game developers do it. That's what singletons for. Well, game developers also like run out with this. This thing from the DLL doesn't free everything from using.
So talked about game developers and how it's just okay to create singletons and then just dump the data. Does anyone see anything else? Here, we'll go. What's up? By multiple what? Oh yeah. So one of them can be accessed by multiple threads. So we have a potential multi-threading problem here on the one on the left. Yeah, because of the if. What did you have?
Actually, both of them have this side. The one on the right, these will be single threaded, but you never really know who actually does get instance first. Unless we put some sort of initialization later or something. Which makes it scary when it does as well.
Okay.
You may never touch it. Maybe you don't cover the code.
So you never actually know who ends up accessing get instance first, and so you can have weird states with whoever accesses it. Yeah. Potential shared mutability as well. Yeah. Yeah. So at C++11, it'd be, yeah.
There were tons of bad things like the double check locking pattern and stuff that everyone got wrong. Oh yeah, about my singleton before 11, right? Yes, but GCC and Clang always make that, let's say.
Yeah.
Only is it running Visual Studio. Only for game developers. Oh, Visual Studio 2017.
So
Sorry.
okay. So pre C++11 wasn't safe in Visual Studio for the Myers singleton. However, everyone else made it safe, but it wasn't officially safe. Does anyone have anything else about these two singleton classes they would like to point out? Cool. So moving on, let's say we're using a singleton. We want to make it a little bit better. And so we're going to take our Myers singleton. and we're going to wrap it. And so we're going to basically templatize the singleton. Who's seen this before? I'm guessing a decent chunk. Okay. So we're going to basically make it so that way instead of holding the instance inside, we're just going to make the instance be a template, and then we're going to be able to make any class we want into our own template. So does anyone have anything else to add with this implementation? So it makes it a lot more versatile, a lot easier to use, and a lot easier to not mess up.
It does require that our singleton type be default constructible, if that matters.
So it matters if you can default construct your singleton type. And then it's a global, so it's probably okay. Yeah. No. So it makes it easier to make a lot more of these. Which, but what if it's still great now? I mean, so there are instances where you're going to want some global data, right? Okay. So are we ready to continue down to the next trend? Cool. So our next trend is dependency injection. Now, the idea with dependency injection is that we aren't going to have this global object anymore, but we're going to inject the dependency into each of our objects that are using it in like 3 different ways. So we're just going to hand the dependency off so that way they can use it and just kind of let them use the object. So with that, when I was figuring out this talk, I felt like I needed to add it aside because I got really confused on the difference between dependency injection and dependency inversion principle. And what makes this really confusing is the fact that in order to do a dependency injection, most of the time people do dependency inversion principle in the process of doing dependency injection. And so you look it up and they line up about the same code-wise, and it's kind of confusing where the line is. So for dependency inversion principle, basically you're going to eliminate your dependency by creating an interface class. And so in this case, we added a plotter interface class and pulled the live plotter out. And this is really nice for testing, but it also reduces your volatility due to your implementation, which is really important when we're doing dependency injection because we're sending it in a bunch of different places. So when we're sending this plotter into a bunch of different classes, the issue is that if your plotter changes at all and your API changes, suddenly you're going to have to deal with that changing in a bunch of different places. So adding this kind of plotter interface can help with that, which is why it ends up happening when you do dependency injection. Cool. So dependency injection. Basically what we're going to do is we're going to inject the dependency into the object in 3 ways. So the 3 ways we're going to inject the dependency in. The first one is interface or template parameter injection. Basically, we're going to inject it via the template at the top and be able to do that in order to get the dependency into the object. The second one is via the setter. So you can do like set plotter and then send it in that way. And the third one is via the constructor. And so you'll do in the constructor, you'll add that in. And this causes you to have one object that's being shared kind of everywhere and you're passing it around. So here's some code. Does anyone have any thoughts on this code?
What does it say if you create a GPS and then don't set the plotter?
You can't.
It requires one on the constructor.
Yeah.
Oh, it's okay, it's replaced.
Yeah. So I did all 3 here. You probably only do 1 in this instance.
I'm slightly nervous about something in general that takes a. Talk to the Rust developers about this.
So slightly nervous about taking and storing a reference. Yeah.
The lifetime of what
Yeah.
Jack has to outlive.
I mean, to be fair, requiring one on the constructor kind of implies that you had one that's going to live longer than the GPS, but the fact that you have the set plotter then breaks that implication.
That's why I don't like sets.
You know,
I prefer construction.
no,
You can pass a shirt.
So
it could be a smart one.
so maybe migrate it to a smart pointer would make it better. Also, what else was there? Potentially avoid using setters.
Storing a reference implicitly deletes certain special interruptions. It's like a I forget which, like two of them, I forget which ones. Two of the.
You can't.
Assignment? Yeah.
It's the,
Yeah, I think it's code assignment operator. Assignment. Assignment. You can't be certain.
yeah,
So potentially reference gets rid of some of the member functions, potentially assignment. So move this to a smart pointer.
or reference wrapper if you really wanted to do it.
Yeah. Yeah.
Someone says, you know,
Or just don't store the reference.
ooh,
Like then you have to understand.
So other option is just only pass it in when you need it, which, yeah,
This also seems like it'd be used with plotting class was an abstract based class because you want to override it for a test. Right?
Yeah. So this is just dependency injection, but like usually you'll add a interface class. Just trying to fit it all in one slide. But yeah. Yeah. So
Right, or something at the end of that plot.
okay.
There and just kind of imply that there's something else that should do.
Okay, I'll do that. So potentially you'd want your dependency inversion principle here, so that way you can do mocking and testing.
The other benefit that means instructors get that you're gonna do a wholly different plotting thing for your testing.
Yeah,
If you template.
if GPS is templated.
Yeah. Template on like team planning.
So
Just for the sake of the recording, you should.
okay,
reading more.
so we potentially will get CTAD for, oh gosh, where
The constructor specifically.
constructor would allow for us to have CTAD.
Yeah, because
If GPS was a template.
yes, you'd have to templatize GPS on plotting.
If GPS, wait, we gotta slip. GPS was templatized on plotting.
For your test. Perhaps plotting needs some sort of real resource. That might test.
So then we could inject a different, I'm sorry, we could inject a different thing. And so that way, if we need a live version, we can have a mocked up version for testing. Cool. Cool. So we're gonna, yeah. But then that conflicts with macros. And so that's kind of worrying.
Is it a technical GPS? But I thought it was GPS.
So we discussed the capitalization of GPS. However, it just gets worse. It'll get worse. It'll be okay. Cool. So as we've highlighted, our alternative to singleton also has some issues here. Doesn't make everybody happy. We still have the problem of this global object that we want to have, and this is just kind of inconvenient. If anything, because we're having to pass plotting and the plotter in everywhere, this suddenly becomes a lot bigger of an impact. And so we've reduced the ability for everyone to access it, but now we've made it harder for the people who need to access it. Like look at your constructor. If you're putting in 3 things, it's going to start to get pretty long, and then you're having to deal with that. Hopefully you aren't having that many global objects, but like worse things have happened. So
You've done it. You laughed too loud.
So potentially we could roll them all into one big God object, would potentially make things worse. But yeah, cool. So then the next one is monostate. Who here's heard of monostate before? Okay. So basically monostate's kind of interesting. So the idea is instead of having a singleton, where your global state is the object, you have inside of it, every object inside of it is static. So that way you have multiple copies that all of the same internal state. So you've kind of moved the issue into the class, which is kind of weird. And so it makes it, one of the pros of it is when you give up on the monostate, it's really easy to transition into individual objects just because you have copies of it running around everywhere. However, it may not work well to replace some of the interface singletons. So if you're doing a singleton that's holding on to an external interface or API, and you need to make sure, it may be harder to move over to a monostate. So here's like a super simple example of kind of how it works. So we have our plot function, and instead of accessing this external interface, we're going to hold a queue and just put all this in the queue and deal with it at the end. And so now our queue becomes static, and we're just going to access our plot function like normal, and everyone can just keep adding things to the queue because it's static, so it's shared throughout every single copy of this class. What's the vibe here?
This is a nightmare. Like, so whether they're all HFT.
So this, hold on, 15 seconds. So this is a nightmare for threading because of the global state.
Because now I can handle the threading in one place. I can make a plug function.
Well, make it safe, but can you make it not content?
Oh,
So potentially because everybody goes through the plot function, it'll be okay, but you still have to deal with contending for the resource.
In the beginning, you mentioned other patterns have a get instance function and how if you like that for your instance, and this could be
Yeah.
makes it
Yeah.
So
So this is harder to tell that you are accessing it because it doesn't have the get instance, so it's not exactly recognizable. Also, if you look at how many people knew what it was, this could totally sneak by someone and you wouldn't recognize it happening.
Plot has a magic number. So you hit it one time or hit it one, call it the next time. That's something totally different, crashes.
So
It's good.
potentially makes it function and not how many times.
So it makes testing really bad because now you have to worry about the state of the plotting queue.
On the previous example, GPS some scale.
But standard CL. Standard CL, every time you think of a state of it, it affects everyone else globally.
Yeah.
I'm not saying it's a good thing.
No,
Yeah.
Flying, horizontal east versus north versus.
So now it becomes harder to distinguish what exactly we're calling with plot. And we're also keeping that global state much like C out, which comes with its pros and cons. Yeah.
This is really bad when it's some things are this way and some things aren't. Like I'm looking at the IO manipulators, for example. No, Jason mentioned CF. You never use good X or anything like that. Which one of them's which ones of them alter the state? Which ones only act for the next output operation? Some way, some of the other. And I don't know. I have to look it up every time, or just not use it. Just not use it.
Sort of like getting absorbed in it's huge. That's the number.
Yeah, what's consuming from this? Like, I could see the producer.
Yeah.
the Consumer.
So hopefully the consumer would be something like, I guess in this instance, what I would think of is like at the end of its lifetime, at the end of the program, we would just save it all out to like a file or like print out a like like a picture with the plot.
So in that case, you have potentially significantly greater memory requirement than you otherwise might.
Yeah.
Because you could like in a different implementation, you could be writing that out to a file on a continuous basis rather than saving saving it until the end. Well, but then what calls? Oh, yeah, like Like now you've got a thing that's like now you need to like auto flush in a thread safe way. Like
Just don't do threads.
I think we're gradually designing a garbage. It's like
So, so to catch everybody online up, we talked about how potentially, because we have this global state, there can be instances where the state isn't actually staying. So like some instances we're preserving it with the static and some other interfaces are not having the static. And so it can be confusing as to what we're ending up messing with, as you can see with some of the things with C out. And then also potentially we're getting closer to garbage collection and that we potentially are using a lot of memory with this architectural decision.
But it was designed to be an interface to whatever handle plotting data.
So it was designed to be an interface to,
Your example was on fluency injection, so.
yeah. Or no, this is monostate.
I'm not following how it is different than a single thing. It's just not that you can't replace the type of. Is the queue the singleton, or is there a larger pattern where the global state is? Is a global instance.
So it's kind of confusing compared to a singleton because you still do have that global state. It's almost like the global state, instead of being the object itself, becomes the inner workings of the object.
Yeah, okay.
And so you're accessing, you have to access through to get to those global objects. So
Hidden global state now.
yeah.
Yeah, I was gonna say, like, you getting all of the disadvantages of classes and objects. Also, because you have to still do all that piping in order to use it.
Yeah.
Which you would normally get with a get engine or something like that, where you just access it from anywhere. But you don't get that.
So you still don't have an easy external access. So you're still having to pass it around.
You thought this was a good idea and realized it.
I
So basically, the constructor becomes your home instance.
yeah.
Right.
So I do not know where it came from. I will figure out where it came from for you.
I can create 10,000 plugins. I don't even have to pass.
Yeah.
I can just construct the plotting cloud anywhere I like. I want to call it any place that I want to call plot.
So you can just
My constructor becomes my get instance.
Yeah.
Yeah.
Does it have to eat through this whole queue? This is like query, to get the current state.
so backing up a second, it's okay. Your constructor becomes your good instance. And then potentially, are we going to have to, if you want to use something with the plotting queue, are you going to have to eat through the queue? Probably. I think there's a lot of issues with this design. Literally.
So who has seen this before? I'm here for my own person. I've never. Same way. You're the only one who's seen it before, so I'm accusing you.
I saw them at. No. It was,
Just call it Shay Singleton.
Oh.
I remember after, it's like, post Java, people started to realize how. And they said, you do this, you get rid of all the getters, just create your object, and you let the compiler deal with the whole aspect of it. And you can just create the instance right there, and then delete it right there with all the different types. And so it was a way of simplifying refactoring code that you didn't actually change it. But what you did is change the immediate use pattern. And so it was presented as a brilliant way to fix a lot of this. That's what I.
But you've never used it, you've just seen it before.
Yeah. I went through and removed a lot of the global stuff, so that's why I said.
So for summary for the online, so with that, kind of like post Java, let me know if I mess up at all, Shay. So post Java, we ended up wanting to get rid of some of the singletons, and so moved to monostate to transfer some of the transfer it. So that way it was moving the global state from the class itself to inside the class. So that way your external accessing align more with what you would expect of an object to make moving over easy, though it became more like a coat of paint.
Yeah, you didn't actually change the real life. Just leaned on their static. And don't quote me on the Java part. I just remember.
Okay.
Dr. Bob.
So don't rely on the potentially Java.
So I didn't know it was called this, but I see object full of static. Actually, I just realized Jason's fault because in part of static everywhere is
That's
now that everyone making on text for statics, a bunch of things look like this.
So
I mean, it's not really not this pattern, but it's still static everywhere because it's on text.
Yeah, but if it's not mutable, it's.
File time.
Well, no, it's static context. Must be initialized. It's not, it's ever, yeah. Not even.
Yeah, if it's not mutable, it's kind of a different thing. Like,
The internals are mutable.
So-
Even if it's complex, that's how things get created.
so now we're talking about context for static.
Which is good, and everyone should love.
Um,
That's bad. I said it's.
do we have anything else to add? Wait, what?
I think a lot of the reason that we ran around in circles is that we tried to use final state to implement an interface.
Oh yeah.
I think this is better explained by using like your data, state data. As opposed to
So potentially using a state instead of an interface in order to describe what's going on here. Cool. So I'm gonna move on. So here's our comparison of our three alternatives for dealing with global state. So we have our singleton. The nice thing with our singleton is we can recognize it. You look at the get instance, you know it's a singleton. It's easy to access. And then dependency injection, it's explicit access and all the pros and all the cons of it. Of you have to pass it around and you have to ensure that everyone has it, but you're also limiting access to it. And then monostate, which is super non-intuitive and it's however, it's easy to transition to individual objects because as Shay said, it's easy to you basically have already decoupled everything pretty much except moved everything inside. So that's a little bit easier to rip it all apart. And it's less powerful than the singleton. So you're kind of giving up a little bit. So it feels like if you're going the global route, maybe go back to the singleton. Like, I think like when it comes down to it, when you're trying to access it, you're able to access the full class has that global scope versus just my computer just died. I should have plugged it in. Yeah.
Fire Sauron.
No, oh no.
My laptop weighs a lot too. So then I think with that, when you have sorry, we're gonna have to wait a second for it to turn on.
Yeah.
So when you have your global state with your singleton, you end up sharing everything as global, which makes it a little bit better versus only having your static objects as global. Does that make sense?
I think I understand what you're saying, but I also feel like that lack of power.
Yeah.
It's the same cache. It's in this because the question of who's the consumer, not the producer, who's the consumer. That consumer has to be given explicit access to that static object to get it presented, right? Where if it was truly a global static object, then everyone could consume and everyone could produce. So you have a slightly more constrained on the interface.
Well, of course, not everybody will add every function to that class.
Well, I'm just saying,
Over 20 years.
yeah, yes. And eventually someone will just add a non-func reference getter for it.
Yes.
Same thing. Don't have to add search after, have that. Move that to C++ object. But the example showed, yeah, maybe you can just change the.
I mean, you're the one who
Yeah.
created it.
Okay.
And making it look more normal, but it's really just global state. You just get rid of a lot of sort of explicit, here's my globe, and then I access my globe when I get it. You just kind of.
Well, since she's getting ready to get this in Aspen, I'm gonna suggest you just put a question mark, less powerful than the singleton, question mark.
Okay.
And then if the talk is moving too fast up to this point. Right there.
Okay. Okay. So yeah.
The creation of the object and the use of the object, we really talk about the construction,
Okay.
which can cause issues, right? It's static and the compiler can decide pretty much the order in which they're constructed.
No, that's not exactly to say that. Statics are constructed in the reverse order of, destructed in the reverse order of construction. And that's guaranteed. The problem is you don't know which order they were constructed in.
Exactly. So you can, they're destructed in the wrong order.
Jason, you've heard.
Yes. Depends on the linkage.
Yes, the only ones that you know exactly when they're gonna be, this is not my thought. The only one that exactly when they're gonna be constructed are the Meyer singleton ones. So they construct on first use ones, the ones that are function local. But every time a static is constructed, it registers in the global handler its structure, and then those are all called in the reverse order, so you don't always just go ahead and
Cool. So I just realized, of course, that's why my singleton exists.
Yeah.
To solve the static
Yeah.
initialization.
Yeah.
Yes.
So to summarize, Meyer singleton is to deal with your static initialization issues. So we're gonna move on. Hopefully this one's easier. So up next we have SPINA and concepts. So SPINA is substitution failure is not an error. I actually spelled it correctly this time, hopefully. So basically our use case for this is function requirements. So we want to be able to break at compile time rather than at runtime. So here's our usage example. So we're going to start off kind of all the way at the beginning. So I'm going to use run Nakata 4, and this basically is a way to approximate a solution to a nonlinear equation. So to figure out kind of what the point would be, or like to be able to send in a set of inputs and figure out what the output is approximately. So with this, our first one, we're constructing it using a double, and that's awesome, and everything's doubles. But then one day you're like, okay, well, we need to use a matrix because, you know, we no longer just have one state that we care about. We care about like position, velocity, and acceleration. So now we're going to send all of those states into our rung Nakata and try and solve it. And so this becomes this. And so now we have 2 copies. Yeah.
So that it broke at runtime, that would break all of the safety.
Doesn't it? Is it?
It's more like it breaks sooner at compile time.
Okay. Sorry. So break sooner at compile time rather than break at runtime.
Get a much somewhat cleaner error.
So continuing, now we've moved to this fancy, we're going to send in a matrix. And now we have 2 copies of the exact same code. And so instinctively, we're going to make it into a template. It looks a lot cleaner. It's beautiful. Except at this point, honestly, I would tend to just be like, okay, we've heard the rumors about Svene. It's a pain to implement. It's a pain to read. We'll just move on and hope no one sends the wrong thing into this function. But so now we're at the point of we want to constrain it. Ideally, I want to make sure that time is a number and output type is able to be added to another output type and multiplied by a number. Those are the 2 things that this function needs in order to be successful, so that way we aren't sending in the wrong thing. So here's kind of our timeline. So we have Svene was in about 2002 is when it was figured out, and then type traits were introduced in C++11, which made it slightly less ugly, and then concepts in C++20. So Svene is constraints on templates. It's known to be really difficult to read, and it's also difficult to constrain. Cool. So we're going to start off really simple and just constrain time. We know time needs to be a number. Awesome. So we can use the is arithmetic v, which is in the type traits, and enable if. Awesome. So this constrains our template and makes it so that way time has to be a number, be it a UN64 or be it a float or a double. Cool. Now we're going to make things a little bit more complicated here and try and figure out this whole output type constraint. Now I tried to do it without using Boost and just build it myself, and that got really confusing and really complicated and was not the vibe. So that's so then I pulled from Boost, and that also means we're having to deal with that third-party dependency, but as well, it's just a little bit ugly. So what we did here is we did is arithmetic v on output type because we need to ensure that if output type is an integer, we need to make sure that we're actually able to do that because we can't have integers or doubles or whatever. But then if it's a class that has overridden operators, we need to make sure that it has a multiply operator and a plus operator that correspond with our use case. And so that's where the 2 Boost lines come in. So what's everybody's thoughts on this? We aren't there yet. So we want time and time step to be maybe 2 different types. Well, for the time being, they're 1 type. We'll just let it be the way it is. Anything else here? Yeah. Standard function isn't const expert capable.
Yeah, I'm just saying it's very good for that function.
Okay. Yeah.
It should be though.
As long as this function isn't part of an overload set, you could get away with using that asserts. You can also write your own.
Could use static asserts and then write our own error message. Cool.
If you're a template anyway, then templatize that function.
If you're a template anyways, templatize the function you're passing in. So maybe pass in a template instead of the stud function. So continuing on, here's the compiler error output for when we break it. So I sent a stud string in. Obviously, we can't multiply a stud string times another stud string, or times a like integer, or times a double, but we can't add stud strings together. So that part works. But like, where are you going to find this in this section of code where the error is? So with this, I feel like the quintessential example of where these really get bad is when we're using Boost. As you can see here,
You definitely need to leave that
Um, so with that, we have at like in the middle, right here, we have boost binary op detail, don't care. Just if you were wondering, we don't care. But also with that, Boost uses a lot of template metaprogramming tricks that tend to come out when we use it wrong and don't realize what we're doing. And then we get nasty warnings and error messages that end up taking up a whole compilation window. And you're just trying to process what's going on. And so that's kind of our quintessential SVN causing a little bit of chaos. So now, concepts. So concepts are name set of requirements. They improve our compiler errors, and they're easier to create custom constraints for. So kind of seeing how it works, here's our first jump. So we're going to have our arithmetic, which is integral or floating point. What's interesting is the standard did not put arithmetic for this, but they have it for type traits, which is kind of interesting. So you have to create your own. And then what's kind of cool is in the template, instead of saying the type name, you say arithmetic instead. So that constrains your template. Cool. So now moving on to our full piece of code. So now we're going to add and multiply. And with that, we're going to basically make it so that way we are fulfilling the conditions that t has to be able to be multiplied by a number and t can be added together. And so t is the same as output type and num is a number. So that's our constraint on it. And then we basically require that that happens. Does anyone have any feelings about this? Does it feel better than this SVN? Cool. So the error looks like this. And so we can obviously see kind of parsing our way down that, oh, t times number is invalid because we can't multiply a std string times like 5. Cool. So now for our comparison, this is one where it feels like it's pretty obvious that concepts made things better. What? However, with that, concepts are in C++20. So if you aren't running C++20, that causes some issues. So yeah.
I have a question.
Yeah.
What if we never use any of these and just pass this in the string to the original? We will get an error and we will understand it.
So what happens if you don't do any of these and you pass this to string in? Yeah.
I don't know what to do. I use the function.
So it'll spit out an error.
You need to constrain one or the other for this, for it not to be ambiguous.
Yes.
Or there might be a case where it gives me, and you actually get street.
Some of it what might have with the change the title, not the
Just like five losing.
So potentially we could have issues where string could multiply and that could cause issues. So that's why we'd end up constraining it to prevent those edge cases from happening.
There, if you only had addition, then the string would work.
Yeah.
You know perfectly well that no one really meant to do that.
Yeah. But it still worked with the concepts. Yeah.
If all you're doing is making a permutation of types, you could write a macro to generate the exact types you support. Spam. Or see that like, then you would just fail to call the function. You get types that you don't support.
So we could potentially move back to a macro. However, that is something that is actively being migrated away from in the majority of production code bases and with the standard.
See, the problem is he's a Rust developer. And they don't want a strong generic type system. We have to use macros. And I'm not wrong. See, he's not arguing.
So, yeah.
templates, at least you can somehow constrain the types of macro everything text or some gibberish.
Oh, yeah.
But
I literally virus my way by writing ridiculous things.
So
So,
Be-
let the air respond.
yeah,
Like, why not have a concept you compile and just let it err on you? The concepts make it clear what you as the implementer of the function or whatever intend to ingest.
Yeah.
So if you just like leave it as a generic type, then you risk like you're not being explicit to your users here. This is what I expect for whatever you're feeding in.
so to summarize, it makes it easier for the users of your implementation to actually figure out kind of what they're supposed to bring in and allows them to figure out kind of what's going on there. So we're going to move on to the next one, polymorphism. So for polymorphism, kind of our use case here is we have one interface with multiple implementations. We have our base class, and then we have two derived classes. And this is something that's used commonly in object-oriented design and is one of the implementations for don't repeat yourself or dry. So basically what you can do is you can move stuff up to the base class and then share that with your derived classes. So we have our virtual functions, and then we have our curiously recurring template pattern or CRTP, and then we have deducing this. Cool. So for virtual functions, one of the biggest negatives with it is it's runtime polymorphism instead of compile time polymorphism, which is really positive for like some cases. Some cases you need the runtime, but majority of cases you really don't. And it's also the quintessential like object-oriented tool in your toolbox. It's the thing that you kind of pull out all the time in order to deal with things, and it tends to be really overused. Because the minute you start going down that object-oriented design pattern, making everything virtual, and then you're suddenly creating diamond hierarchies, and you're doing a bunch of interesting stuff. So with that, here's kind of the original code. And this is hopefully code that everyone's kind of familiar with. We have a pure virtual function, and then we have two functions below it that both create the pure virtual function, and then we're calling that in the base class. Awesome. What's really nice about this is we're actually able to tell what's virtual and what's not in this inheritance via override and via virtual, which are two. With override, you can actually turn on a compiler warning to verify that that override actually exists. So it's really easy to see and identify for the users writing the code. Does anyone have any other feelings about this? Cool.
You're not forced into.
So you're not forced into heap allocations of all the objects. Maybe.
I can still pass on the stack.
Yeah.
You can create a TCP on the stack and pass it to some function that requires less.
As long as it requires TCP and not a network connection.
No.
No.
I mean, you have TCP on the stack. Now, if you want to go from
Okay.
we did that.
So we can create a TCP and do whatever we want with it without having to put it on the heap, right? Cool. Yeah.
The price of pure virtual functions is you're imposing the requirement that everyone who uses this interface has to implement all of the virtual functions.
Yes.
Yep. And that, when left unchecked, that can be a
So we're forcing everyone to have to create this pure virtual function who ends up inheriting from it.
Yeah, so just a generalization of that. Liskov substitution principle cuts both ways. The only things that can inherit the network connection are things that are network connections in every possible logical way, which is great if that's what you want. But it means that something that is only mostly a network connection, you put that in your or more likely some other course. So 6 months down the road, he tries to do something with what he wrote. Gets over.
how do you get boats which are actually deriving from planes?
Yeah.
You know,
Oh.
hierarchy.
So
All birds can fly, penguins are birds, penguins can't fly.
So
Great example.
Right.
This one is like, everyone wants to do this.
yeah.
Because does the opposite.
So because they're not the same, you have inheritance issues of because we're forcing that pure virtual, or even if we aren't enforcing the pure virtual, we're creating this hierarchy that potentially doesn't correspond with what's actually going on.
But you have also the multiple layers and layers that end up kind of requiring one attribute, like layer one or something. Think of SCTP, I could think of other external products, even multi-path, TCP, all kinds of things have weird things which they would share with TCP, but would not. And now we're all constrained through one little linear hierarchy, which will have some things reproduced and some things not shared at all. Curiously repeating template pattern actually almost makes more sense.
So we're kind of forcing this linear hierarchy with all of our items.
And also, you solved a problem here by moving the construction to an init function.
Yeah.
Because if you wanted to construct using initialize config in the network, you could.
So we moved everything to the init function in order to deal with. Because we can't call it.
I mean, to restate, the really J, and then class hierarchies tend to get unwieldy because they get driven more by the desire to share code than an actual principle like is a relationship with you.
So we're trying to share code so much instead of worrying about the actual relationship.
Compilers are quite bad in general with devirtualization. So you're adding another layer of indirection, potentially expensive. Worked on a project where I worked on it about 20% in.
So virtualization comes with a super high cost. Potentially. Okay.
Sometimes, especially modern compilers can see through it and do, I'd say occasionally, but for the most part, but yeah, you're asking for a layer of interaction, and the compiler will sometimes.
So we're going to keep going. So up next we have CRTP, which is compile time polymorphism. And basically how it works is we're forcing a downcast from the parent to access the child elements. And this is a explicit cast, which is really nice as well. So we're basically saying, okay, here's our parent object, and inside of our parent object, we're going to do a cast to the child, and then that's how we'll access the child's parameters. So this is how this looks. So we have that static cast derive of this pointer, and then that allows us to access the child's objects. Cool. Does anyone have any major thoughts here? Yeah. So we can have issues with multiple inheritance levels. We'll hold on, we'll get there. Okay.
This basically only works well for one level. Try to derive now again from unity, and you have to pass through.
Yeah.
You can do it, but really get complicated.
So then really good for only one level. Okay, so we're going to move on to deducing this. Deducing this is a C++ 23 feature, and it simplifies compile time polymorphism and makes it a lot nicer. So here's kind of what it looks like. It's a lot nicer. We got rid of the template with the multiple different templates that are all kind of referencing each other, and is kind of that circularness, and it looks a lot nicer. Does anyone have any major thoughts here? Cool. So with that, we do have this. What's up?
I mean, the issue here, potential issue here, and it's probably the same as the other is, if you're doing static polymorphism, that can only work with the type that it can look like you have dynamic typing,
Yeah.
and you don't. So you can't pass around the point to a network connection and express.
Yeah. So you can't pass it around.
If you're a template function. Yeah, for the argument technique.
Yeah, you have to stay in static typing.
Yeah.
This really is.
Okay. Yeah.
Well, we can talk.
Changed. But really, it's that.
Yeah. So it's really not super polymorphic because it's static because you're doing it all at compile time.
In theory, there's reading code somewhere.
Yeah.
It just gets inlined over.
Okay.
So it costs more in terms of code space.
So,
I mean, that would be.
so moving on, I guess. We're now going to do multi-level inheritance, which is what everyone wants to do. And so what we're going to do is I have one for each of them, and you're going to guess what the output is for session B. So this is your quintessential virtual, we got our overrides, life's good, we're printing something out. So who thinks that session B will output TCP? Raise your hand. Who thinks it'll output session? Okay, we'll give a minute, sorry. Okay. Okay. Is everyone good? Okay, so who thinks it'll print TCP? Who thinks it'll print session? Cool. Yeah, print session. Yeah. so, so now on for the second one. Now we did it with CRTP. So with CRTP, it gets really weird when you add a second level. Can I get like thumbs ups when everyone's finished reading and knows what is happening? Okay. I think we're gonna go with a vote now. So who thinks that session B will be TCP? Raise your hand. Who thinks it'll be a session? Okay. So this is TCP. Because of the pointer at the top is going to the derived class, not the derives derived class. And so because we had to add that other layer, it's not going all the way up like we would love it to with our virtual. So yeah. Cool. And then deducing this. Yeah.
You have to poke inside to find out what.
Yeah. So you're gonna have to do an is same on it to check if it's actually void to verify that you haven't done that, and then you can do your static cast to your T in order to figure out what your T type is. Does that make sense? Yeah. So this is definitely not ideally how we would like to deal with things and is making things a little bit more complicated. So now deducing this. I'll give you all a minute to take a look at it. Give me a thumbs up when you figured out what's going on here. Okay. So who thinks that this is going to display TCP? Raise your hand. Okay. Who thinks it's going to display session? Awesome. Okay. Yeah, it displays session. So because it's doing deducing this, it's going to go to the furthest down child, and so that's how we're going to get session out of this, which is more of what we would expect out of our like polymorphic behavior just in compile time, which is a lot better than what we were dealing with CRTP. So when we're looking at comparing all of our different alternatives, we have our runtime polymorphism, which is really easy to trace, our CRTP, which is a lot harder to trace and a lot harder to read because we have all those template parameters and we're passing it around. And it also is really difficult to do multi-level polymorphism, kind of inheriting up the tree, even at compile time. And then deducing this does a better job at having that compile time. However, it's also hard to trace because you're relying on that self. And so you have to make sure that people know what's going on versus with our virtual and our override keywords, that's really obvious and really apparent to the reader. Cool. So with that, kind of concluding and wrapping up, doesn't really feel like newer is always better. Seems like there's some things where we have new technology and new techniques that make things a lot easier to do, make it a lot easier, but we need to consistently reevaluate our alternatives and figure out, is the newer thing just a coat of paint, as well as our use case determines our usability. So if we have to use a global object, it's probably best that we go back to using something like a singleton, although there are newer options. So like potentially those newer options, depending on our use case, isn't actually the best way for us to go. Are there any questions? Cool, thank you.